This is problem 8-13M. It's on page 444. Let me copy down the cross-sectional area. I chose this one because it's more than just rectangles. There are some, I don't want to say hemispheres, but half circles at either end. The spacing here is 0, well, let's see. I would rather work in meters, so 0.19 meters. The overall height is 250 millimeters, which is 0.25 meters. And then the thickness of this thing, or the width, is 60 millimeters, so 0.06 meters. So obviously the radius here is 0.03 meters. Okay, and all that would make sense, because if we take 0.06 from 0.25, we'd get 0.19. Now the shear applied to this is 71.2 kilonewtons. And we'd like to find out the maximum stress. Now, what do you think the maximum stress, or where do you think the maximum stress, the maximum shear stress will occur? Center. Right. Well, how do you know that? I mean, there is a thickness out here that's less.
It doesn't change.
It's part of a circle, so it's not, if a regular circle, right, does not change quickly enough for the shear thickness to go down quick enough, this isn't either, right? This isn't going to change quickly enough. So we're sure the shear will be the maximum in the center. And we're not going to prove that, but I'll just state that. So we'd like to calculate it. So again, we're going to use the general equation. It would be VQ over IT. Okay, so we need the area moment of inertia, we need the thickness. The thickness is easy, that's no big deal. So we're just calculating area properties in order to solve this. Yes?
Could we possibly, because you gave us special shear formulas for a rectangle and a circle, since we got one whole circle there and we can split the rectangle, couldn't we just add those two together?
Could we add them together? That's a great question. The problem we have is that this piece is not a circle. You could put them together at the central axis and say they're circle, but they're not. They're separated off, and so their Q product is different. Does that make sense?
Yeah.
So I don't think there's a real easy way to do it. You could probably find some way to do it. I don't know what that would be.
I was just wondering if it would be easier.
Well, ideally, sure.
Yeah.
Yeah. Yes.
There's an equation for a semicircle.
There is an equation for a semicircle. Where is it? It's in the back of the book.
No, it's right next to the one.
Right next to it. Okay. If there's an equation for a semicircle that's away from the neutral axis, that would help us quite a lot. I didn't notice that as I looked through this. Do you know a page number?
I thought it goes by the ones that you gave us.
Sorry?
The one by the square and circle.
The rectangle and circle.
Page 435.
Is it page 435? Is that the one you're thinking of?
Yeah.
Okay, I don't think that's going to work because that's for a circular section. Because what we have is a section where the half circle is away from the neutral axis. Does that make sense? That was a good thing to bring up because probably everybody else was thinking the same thing. So it's good to bring that, but I don't think that would work. We could try playing with it, see what happens. But let's get through this first and then we can continue. Okay. All right, so let's go. We're going to need some information, and it may be difficult to deal with this, except that at the back of your book, the first part of the appendix, 690 and 691, has some very valuable information. Go to page 691, please. We do have to deal with some half circles. The rectangular portion is easy, right? But the half circles are the hard part. So let's get some information about half circles. Let me just sketch one down here. Not a very good half circle, but there it is. The distance to the centroid of that area, they call it y bar. I'm not going to do that because our y bar will always be from the neutral axis to the center of the area itself. Does that make sense? So I'm not going to call it y bar, but I am going to write down the equation. They say that it is 2 times the diameter divided by 3 pi, which if you put all the constants together, comes out to about 0.212 times the diameter. Is that what you guys have? I know there are some mistakes in the printings of this book, so God only knows if that's right. By the way, a student came to me before class and I recommended he look up the errata for the book. Errata, I always spell it wrong. I spell it E-R-R-A-T-T-A. It's E-R-R-A-T-A. So it's like error, but with a T in it, almost. Okay, so anyway, there's the distance, excuse me, to the centroid of that area at the end. Excuse me. Now, what particular area do you think we would be using for calculating Q? Let me go ahead and write down Q again. Q is a particular area multiplied by the height of the centroid of that area. Okay. And by the way, to calculate Q, the easiest way to do it for our purposes is to calculate, we call it A1 Y1 plus A2 Y2. Okay, we don't actually have to find the centroid of the combined area, which would be a big pain, and then multiply by the total area. This will give us the same thing. So basically what I've done is I've broken this up. Let's use some human factors here. A1 Y1 plus A2 Y2, where A2 will be this area, and A1 will be this area. Okay? All right. So getting the area is pretty simple. In fact, I'm not going to use the red pen because it's running out of ink. But let's go ahead and get A1. What would A1 be? Well, it'd be 0.6 multiplied by half of 0.19. Okay? So throw that into your calculator, please. And let me know what A1 is.
Did you say 1/2 of 0.19?
Half of 0.19 times 0.06, because we're interested in the area of that rectangle.
0.0057.
Any second of that one?
I just got point zero
Yeah,
five
one too
seven.
many zeros.
One too many zeros? Is that okay now? Everyone agree with that or no?
0.5 times 0.19 is 0.095 times 0.06 is 0.0057.
I got .0057 too.
We're split. Let's try one. Those of you that got .057, try it again, but it sounds like more people are getting 2 zeros, 5, 7.
All right.
Okay. All right, so there we go. So there's area 1. How about this area, A2? What would it be? Well, we could calculate the area of the circle and then divide it by 2. Right? So pi r squared over 2. So pi, what is r? Well, it's 0.03. So multiply pi by 0.03 squared divided by 2. What do we get for that?
0.0014.
Trying to write square inches. Okay, so there's the 2 areas. What about the centroid? Well, the centroid of A1 is pretty easy, right? In fact, let's go ahead and start filling it in. Or I tell you what, let's just write it up here. Y1 and Y2. Let's calculate Y1. Take 0.19 and divide it by 4. How much is that? It's less than 0.05, but I can't do that in my head.
.0475.
Okay, there's Y1. How about Y2? Well, Y2 is a little more tricky. We've got to take half of 0.19 and add to it 0.212 times 0.06. Okay, so let me write that out. 0.19 over 2 plus 0.212 multiplied by 0.06. And both of those are meters. So what do we get for this?
0.108.
Oh, wait a second, I'm sorry. I said by 4 and then I wrote by 2. So we need that. No, that's right, it is by 2. I'm calculating the centroid of that area, so I do need half of 0.19. There we go. I'm sorry, how much was it?
0.108.
0.108 meters, thank you. Okay, so now we can calculate Q. So A1 is 0.0057 square meters multiplied by Y1, which is 0.108 meters, to which we will add A2, 0.0014 square meters, multiplied by, what did I do here?
Why do you have to multiply by 0.06? If it was, you already solved that item.
What's that?
We already solved the 0.212 as the y bar. Why do you multiply that again by 0.06? If that was already the distance.
Are you talking about this section right here?
Yeah.
Okay, because 0.212 times d, probably that looks like a 0 to you. I'm trying to make a d for the diameter. So the answer is not just that this distance is 0.212, it's 0.212 times whatever the diameter of that circle is. Does that answer your question?
So you have the 0.212 is not the actual y bar.
No, 0.212 is not the y bar, it's 0.212 times d, where d is the diameter of the circle. Good question. Does that make sense to everyone? All right, and also I mislabeled my Y1 and Y2. I was going too fast and messed up. But I think the numbers are,
It come out.
wait a second, did I mess up here? I did mess up. This is Y2 and that is Y1. Yeah, so I should have those two flipped, I'm sorry. So this one goes up here and that one goes down here. Let's try again. All right, so I need A1, which is this, multiplied by Y1. Yeah, that makes more sense. 0.0475 meters. I don't know how I did that. And then A2, which is in fact this area, and the distance to that area is this. So times 0.108 meters. Okay. So multiply those together and add the product of these two. What do we get for Q? Everyone's calculator tired. I see questioning looks. Have I made another mistake along the way?
Getting 4.22 times 10 to the negative 4.
I got 4.22 times 10 to the negative 4.
I only say it.
Everyone's scared to say it. Oops, not meters squared, that's meters cubed.
Negative.
So it sounds like we're in negative 4 things. So it sounds like we have agreement on Q? So that takes care of Q. How about I? How about the cross-sectional area moment of inertia? Well, for that, what I would like to do is use my spreadsheet. And let me just make some notes here. I'm going to copy this. Copy, create a copy, and of course I'll post this as well. This problem was the last one we worked, which was 8-11E. And the one we're working now is 8-13. Okay, so we will have, again, 4 areas that will contribute to the area moment of inertia. Probably shouldn't have done that, but that's okay. Let's see, the areas, let me start off with the area at the bottom, the lowest half circle. And fortunately we have a spreadsheet so we can calculate all of this. So the area is simply pi. And I'm going to use the equation that your author has in the text. Go back to the appendix, page 691. You'll notice he has an area equation. It's pi d squared over 8, which is the same thing as pi r squared over 2. Okay, but I'll just use it because it's in the book. That way you can tell where it comes from. So 0.06 squared is the diameter, and then divided by 8. So there's the area of the lower half circle. The distance y is now going to be the distance from the bottom up to the centroid. Now we have to be careful there. This distance that they've given us is exactly opposite of what we need. Does that make sense? We need the distance from the lower tangent point up to the centroid. So what I'm going to do is take the radius, which is half the diameter, less this amount. Does that make sense? So equals the radius, which is 0.06 over 2, and subtract off, so now I've got this distance, I'm going to subtract off this distance so I get this distance. Okay, so minus 0.212. I'll go ahead and use the 2d over 3 pi since I've got Excel here, and it won't complain about doing all the math. Well, it might crash. So minus 2 times the diameter divided by 3 divided by pi. Okay, so there's yi, and there's the product of the two. Now I need the moment of inertia. So look on page 691. Should I use ix or iy, and why?
I sub x.
I sub x, I agree. Why is it I sub x? Because that's the way the axis is running that I'm interested in, okay? All right, so ix will be equal to let's see, 0.00686 times the diameter, 0.06 quantities squared. No, to the fourth. Not squared, that would give us the wrong units. Okay. Now, again, let me just go ahead and take care of the semicircle at the end, except that now y is different, right? Now what is y? Well, now y is the distance from here up to the centroid of that area. Okay? So that's going to be 0.06 plus 0.19 plus this. Okay? Let's do that next. So 0.06 plus 0.19 plus, and I'll use 2 times d, 0.06 over 3 over pi. Okay, now let's take care of, let's see, you know, really I don't have to have 4 areas, I can have just 1 area here. That'll be quicker. So let's get rid of one of these rows. Renumber that one so it looks decent. So now let's deal with the large rectangle. The large rectangle has an area of 0.06 times 0.19. The center of that area is at 0.25 over 2, because the overall height of this thing is 0.25. Okay? And then the area moment of inertia is 1/12 bh cubed, about its own centroid. Okay, so that's going to be 0.06, that's the base, times the height, which is 0.19 cubed divided by 12. Okay? So finally, we've got the area moment of inertia. And as I said, I recommend you use this spreadsheet because it'll save you a lot of difficulty. Here's my marker. So what we got was 7.76 times 10 to the negative fifth. Let's plug in everything. So we've got 71,200 newtons, 71,200 newtons times Q. Q is 4.22 times 10 to the negative fourth cubic meters divided by I, which we got from the spreadsheet, 7.76 times 10 to the negative fifth meters to the fourth, and then T, the thickness. Well, we're interested in the shear in this area, right, at the neutral axis, so that is 0.06 meters. So plug that into your calculator, please. We'll finish off this problem. The units we'll end up with is pascals, because we've got newtons per meter squared. Notice that all the meters cancel except for 2 of them in the denominator. So we'll have pascals. Anyone have a number?
6.45 megapascals.
6.45 megapascals?
Yep.
Anyone agree with that? Second it?
Yeah.
Okay. So there's the shear stress at the center of that cross section. All right, questions, comments? Yes,
The book has 7.46.
it does? We've done something wrong along the way. Unless they did something wrong, which is also possible. There are mistakes in the book. I don't know which it is. I'll try to go back through this. I'll write out the solutions later on and I'll be a little more careful. And then we'll find out. If there's something wrong here, I'll put a comment on the video and correct it. And we may have made a mistake in calculating our area somewhere, but the procedure's correct. Okay. Any other questions? Yes?
Don't forget about Danny.
I won't forget about Danny.